Morning everybody. Today we will be starting a new topic to find the solution of a system finding its Schrodinger equation and find the solution of a system. So here last classes we have studied the perturbation theory, degenerate case and non-degenerate case. Now we are going to a different topic to find the solution for some difficult systems which we cannot find real solution. So the principle, the topic here is the variation principle. The technique we use here is variation principle. So here what we do is we just select a wave function. We just guess a wave function. We take a normal wave function and say that it is the eigenfunction of the system. It is the solution of the system. But we don't know whether it is real solution, exact solution of the exact wave function of the system. And then we find out the energy of the system. So the energy eigenvalues will be the solution. So when we have to find the ground state energies, for example, if you want to find the ground state energy of a particular system, e.g. Of a system described by a Hamiltonian which is unable to solve. So it's the system has a Hamiltonian which is little complicated. So if we are unable to solve that Hamiltonian to find the energy eigenvalue, then we use the variation principle, and we will it will get you a value. If you do the variation principle, it will get you a value for the solution which is very close to the exact solution. So we don't know whether it is the exact solution, but it should be very close to the exact solution. We will do that in an example. Okay, you just understand the principle here, what principle we are using. Okay, so we claim that the solution, that is the ground state energy, here we are taking let it be the solution be a ground state energy eigenvalue which is the ground state energy Eg, and we take the expectation value of its Hamiltonian in the state psi. See that Eg is less than or equal to expectation value of Hamiltonian. That means we don't know whether it is exactly the Eg value which we are going to get when you do the expectation value of Hamiltonian. So we'd say that it should be greater than or equal to Eg. Okay, so it can be equal to Eg or it can be greater than the value of Eg. So we are going to find out the Hamiltonian expectation in the state psi, where psi we take as wave function which is a guessed wave function. We are taking it as a guessed wave function. We don't know what is the eigenfunction. So we just take a wave function and say that it is the eigenfunction of the system. So we are just taking a trial. So this wave function should be normalized. Okay. So equation 1 we have written that expectation value of H is Eg. So equation 1 is just an estimate of Eg, as we have not selected the exact eigenstate of ground state energy Eg. We didn't take the value exact eigenfunction, so we took only a guessed wave function psi. So psi may be one of the excited state. Maybe it is not the exact eigenfunction of the energy Eg. So maybe it can be the wave function of the higher energy level. So psi may be one of the excited state, so that H expectation is exceeding Eg. So if psi is the state which represents the higher excited state, then its expectation value of H in that state will be always greater than Eg, isn't it? So that is why we say that it can be equal to Eg or it should be greater than equal to Eg, the ground state energy. So that is why we take here the ground state energy of the system. So if you take the expectation value of Hamiltonian, always it represents the energy, but it can be maybe it it will be representing the value of ground state, or it will be higher than that. So that is what we are going to check. So as psi is an eigenfunction of H, it forms a complete set. So you have taken the wave function psi, which is the eigenfunction of H. So it can be represented as a linear combination of different wave functions psi n. So we can write it as psi is equal to sum over n Cn psi n. And when we do the operation equation, eigenvalue equation, which is H psi n is equal to En psi n, where En will be the eigenvalue of H, Hamiltonian. And as psi is normalized, you know already that psi star is 1, or inner product psi is 1. So you can write substitute for psi there, sigma n Cn star Cn. Bra psi n will be Cn star. Bra psi will be sigma n Cn star psi n, and ket psi n will be sigma n Cn psi n. Ket psi will be sigma n Cn psi n. So if you substitute that, it will be sigma n Cn star Cn inner product psi n, which is 1. So you will get sigma n modulus of Cn square, which is equation number 2. So this is the value of which is equal to 1. It should be equal to 1. Sigma n Cn modulus square is equal to 1. That is equation number 2. Okay, equation 1 we have, equation 2 we have. Now let us substitute for H. So H, equation 1, in equation 1 we have written the expectation value of H, which is equal to, after substituting for psi in terms of psi n, you can write it as, we have substituted psi as sigma n Cn psi n. So that is sigma n Cn star Cn psi n into En. En will be the eigenvalue. So the answer will be psi n is 1. So sigma n Cn modulus square En will be the value of expectation value of Hamiltonian, and it is represented here as equation number 3. Understood? Okay, now here we can say that as sigma n Cn modulus square is 1. We have already written it in equation 1. So H, expectation value, always represents the value of energy, isn't it? So it can be, it is En, isn't it? The H expectation value is En. I have not written there here. After equation 3 you can write as expectation value of H is equal to En, only En, without sigma n. Sigma n Cn modulus square is 1. So H expectation value is En. So En can be equal to Eg when n is equal to 1. So or it can be greater than Eg. So we can always write as H expectation value is equal to or greater than Eg. Equation number 4. Okay. And Eg is the smallest eigenvalue. So this is the theory of variational principle you have to use in different systems. So remember, what you want to do is you just need to find the expectation value of H in a guessed state psi. So we just take a guessed trial wave function psi, and we take the expectation value of Hamiltonian to find the energy eigenvalue. And then now let us find the ground state energy. We take an example. Let us find the ground state energy of a one-dimensional harmonic oscillator. This is an example for finding the solution using variational principle. Okay, so ground state energy of one-dimensional harmonic oscillator. See here, we have written the Hamiltonian there. It is kinetic energy plus potential energy. Potential energy for harmonic oscillator, we know that it is half m omega square r square. Here it is one dimensional, so we have written it as half m omega square x square. And kinetic energy is minus h cut square by 2m d square by dx square, which is minus h cut square by 2m del square. Del, as it is one dimensional, del square becomes d square by dx square. Understood? P square by 2m form is the kinetic energy. So equation number 5 we have written. Hamiltonian we know. Now we pick the guess the trial wave function here, which is the Gaussian wave function, and it is equation number 6, where psi of x is equal to a into e raised to minus bx square. See that it is the Gaussian wave function. We just take a wave function which is the trial wave function, where b is a constant there. Now let us find the value of here value of a should be found out. A into e raised to minus bx square is the wave function. So we need to find the value of a there. And if you want to do that, you have to normalize the wave function. So by normalizing we get psi star or psi inner product is equal to 1. And when you substitute for psi bra and psi ket, you will get a modulus square. A comes 2 times, so we take the modulus of a square, because psi bra and psi ket it should be even if it is having complex quantity, c star c, it will come c star c, isn't it? So a star a, it will come. So a if a is complex, it should be a star a. A star a is a modulus square. A star comes from the bra psi and a comes from the ket psi. Okay, so a star a will be a modulus square, and that is a real number, and that is a constant. You can take it out from the integration, and the remaining 2 terms will be e raised to minus bx squared comes 2 times from the bra psi and from the ket psi, isn't it? So integration minus infinity to plus infinity e raised to minus 2bx square into dx will be the value of psi star psi, which is equal to 1. So we know that it is equal to 1. It is normalized the wave function. So when you take the integration of e raised to minus 2bx square from minus infinity to plus infinity, it is a value, it is a particular defined value which is equal to root of 5 by 2b. Remember that. So when you do that, you will get a modulus square into root of pi by 2b is equal to 1. From that you can find a, which is 2b by pi whole raised to half. Understood? That is equation number 8. Now we have already found out a. Now we just need to find the expectation value of Hamiltonian. For finding the expectation value of Hamiltonian, we need to find out separately the expectation value of kinetic energy and potential energy. So H expectation is equal to T expectation plus V expectation. So let us just find out the first one, T expectation, which is minus h cut square by 2m psi d square by dx square psi. And it is equal to minus h cut square by 2m a modulus square into integral e raised to minus infinity to plus infinity e raised to minus bx square into d square by dx square of e raised to minus bx square into dx. Okay, so when you take the value of integration there, you will get like this. It will be, see that it is h cut square by 2m modulus a square into b by 2b by pi square root root of 2b by pi. Or you can, it is divided, so you can either otherwise write b into root of pi by 2b, and that will be minus also. So remember the answer of this is also a identity. When you take d square by dx square and d raised to minus bx square, you can do that, and it will be I think you can do that, 2b e raised to minus bx square, it will be like that, I think, or b square e raised to minus bx square. So 2 times it will be e raised to minus bx square into 2bx is like that it will come. So that will be also an identity, and you remember that you should remember that integration of that identity should be b into minus b into root of pi by 2b. Okay, the other one was root of pi by 2b only. Here it should be minus b into root of pi by 2b. Here there will be x. X will be coming as a product there. X into e raised to minus b x square will be there. That is why this another identity. So you cannot just write it as root of pi by 2b. It should be minus b root of pi by 2b. So after substituting that, you will get like that h cut square by 2m modulus a square b into root of 2b by pi. We know that a is a modulus square is 2b by pi square root. So that we can cancel it each other. As a modulus square and 2b by pi square root get cancelled. A modulus square from the numerator and 2b by pi square root in the denominator. It will get cancelled, and t expectation will be h cut square b by 2m. So from 8 we are substituting for a there in the above equation, and you will get like that. T expectation is h cut square b by 2m. Now let us go to the to find out the expectation value of potential energy. Here also there are constants. Half m omega square modulus a square, we can take it out, and integral minus infinity to plus infinity raised to minus 2b x square x into x square. This is also an identity. You can write it as half m omega squared modulus a square into 1 by 4b. It will be 1 by 4b root of pi by 2b. 1 by 4b root of pi by 2b. The other one was minus b root of pi by 2b. So this is 1 by 4b root of pi by 2b. These are all identities. The integration, you have to remember those values. So V expectation will be after cancelling a modulus square and root of pi by 2b. And then you will get m omega square divided by 8 into b. That will be expectation value of potential energy, equation number 10. Now let us add these two. You will get expectation value of H, which is h cut square b by 2m plus m omega square by 8b, which is equation number 11. So we know that this should be either equal to Eg or it should be greater than Eg. So this exceeds Eg for any b value. We know that. So in order to find the value, exact value of Eg, we need to take the derivative of the h expectation, because when you take the derivative of h expectation with respect to b there, if the minimum point, at the minimum point will be the eigenvalue Eg is in ground state. So minimum, when you take, then the derivative should be 0, isn't it? So minimum will be if the energy value is a curve, at a minimum and maximum points, if you take the derivative of it, it should be constant 0, isn't it? So we are taking the to find out the lowest energy, we take the derivative of h expectation with respect to b. So b is the variable there. For any value of b, this h expectation will be either equal to Eg or greater than Eg. So in order to find out the lowest energy, you just take the derivative with respect to b and find it to equate it to 0, and you will get the value of b. Value of b for ground state energy. Okay, so d by db of h. Here d by db of h expectation, you get h cut square by 2m plus it should be minus m omega square by 8b square, isn't it? So it is equal to 0. It's equated to 0. From that you can find out B is equal to m omega by 2h cut. Okay, now let us substitute this back to the equation number 11. Equation number 12 is substituted back to equation number 11 to find out the value of Eg. So that will be the minimum energy. So if you substitute that, you will get H minimum is equal to, after substituting the value of B there, h cut square by 2m into m omega by 2h cut plus m omega square by 8 m omega by 2h cut. If you cancel all the values and add it, it should be half h cut omega. This is the exact ground state energy which we have already seen in one-dimensional harmonic oscillator, isn't it? So n plus half into h cut omega, n is equal to 0 means it is the ground state energy and it is half h cut omega. So that is the solution of one-dimensional harmonic oscillator, which we have already seen or we have already found out in earlier chapters, in earlier classes we have studied that, isn't it? So using this variation principle, we could find exactly the eigenvalue of, or energy eigenvalue, which is the ground state energy of the one-dimensional harmonic oscillator. So we have found out the solution Eg. Now let us go to a different example, which is ground state energy of the delta function potential. This is another state or another system. Its Hamiltonian will be minus h cut square by 2m d square by dx square minus alpha into delta x. Here delta function potential is delta function, so we can write it as a constant into delta x. So the potential energy is a constant into delta x. Equation number 14. Remember this. Now we are going to find out, we already found out the value of kinetic energy expectation. You can take it from the previous example. Now you just need to take the expectation value of potential energy, and we take the trial wave function here, the Gaussian function itself, which is a into e raised to minus bx square. And if you find the potential energy expectation, it will be minus alpha modulus a square minus integral minus infinity to plus infinity e raised to minus 2bx square delta x dx, isn't it? So that integration is equal to 1. Remember that. So we can write it as V expectation is minus alpha modulus a square. And a modulus square we have already found from the previous case. It is 2b by pi square root. After substituting, it is minus alpha 2b by pi square root is the value of potential energy expectation, which is equation number 15. Okay. Now we know from previous section, kinetic energy expectation is h cut square b by 2m. It is from 9. Now add these two. H expectation will be h cut square b by 2m minus alpha root of 2b by pi, and it should be always greater than or equal to ground state energy. And if you need to find exact the value of Eg, you just need to take the minimum point. In order to take the minimum point, you take the derivative of this h expectation and equate it to 0. So minimizing h expectation, you can take the derivative dh expectation by db is equal to h cut square by 2m minus alpha by root pi into root 2 b de square root b de derivative. Its derivative is 1 by 2 root b. So if you do that, it will be h cut square by 2m minus alpha divided by root of 2b pi. And you have equated it to 0 because minimizing the derivative will be 0. So if you equate it to 0, you will get root of b as 2 alpha m by root of 2 pi h cut square and b as 2 alpha square m square divided by pi h cut raised to 4, which is equation number 17. So B we have found out for getting the value of Eg. the lowest energy eigenvalue. So H minimum will be, you have to substitute B there in equation number 6. So it will be 16, equation number 16. Substitute 17 in equation number 16, you will get Eg. H expectation minimum, which is equal to, after substituting, cancelling the values, you will get Eg is equal to minus alpha square m by pi h cut square. And this is the solution for the delta function potential, the ground state energy. And we know already the value solution ground state energy, which is equal to minus m alpha square divided by 2h cut square. So this is a little difference found out from the variation principle. Instead of 2, it is pi there. But we know that equation 18 is obtained by using the trial wave function, isn't it? So it is little bit greater than 19, and as pi is little bit greater than 2. So we got the solution, but a small difference is there. But still it is very, very close to the exact solution. That's all for today.